Hi, this is the Tempter podcast where we discuss embedded Linux, IoT development, and anything else we find interesting. Your hosts are Kem Raj and Cliff Brake. Today we're going to discuss application development in the context of embedded Linux and some of the things we've learned over the years, preferences we've come to, and also the different types of applications you might write. So anyway, to get started, Kem, why don't maybe you could just share some thoughts on applications in the context of an embedded system?
Right. Hi, Cliff. Applications in embedded Linux is an interesting topic, and I think it's important to make a difference between, say, embedded Linux system or a desktop system or a server system. And in general, there are different types of applications that you deploy the systems. So predominantly, you will find there are real-time systems in which are having deterministic latency needs. And you got standalone systems which are not connected to other systems via some networking or other ways to connect. And then you got connected systems, which is most of these days. You got IoT systems, and so they connect with each other or to a backend. Of course, the largest part is the mobile development. And predominantly, these are types of embedded systems, and the design of applications on this go hand in hand with which type of embedded space you are targeting. So I think what we know about them is many of the common pieces there. Of course, you got abstractions on top of various middlewares or operating systems. So that's my take on what a application would look like. So I know that typically people are exposed to their desktops and servers, and so they have a view of what a system should look like. So what do you see embedded system look like from its anatomy perspective when you see a point of sale equipment running or a farming device that is mounted on a tractor running? So how would you kind of divide that from a software perspective that you could see that what is running on this particular device?
Yeah, maybe to back up a little bit. Sometimes I don't have a technical definition as to what is an embedded system, but typically in the context of my work, it's just more of a computer system that does one specific task, whether it's collecting data or it's instrumenting equipment connected to an agricultural tractor or a number of other things. So that kind of differentiates, at least in my experience, kind of what an embedded system is from like a desktop computer or a general purpose server.
That's well said, actually.
And I guess one other thing we might want to back up and discuss is when do you use Linux in an embedded system versus like an RTOS or something else?
Mm-hmm.
Because that's a critical decision point.
Yes.
And something you need to ask the question.
Right. Yeah. So I think perhaps my view, for example, in there is based upon the application that you have. Say, if you were to do sensor, right, that is doing one task and it has to live in a unmonitored location, right, and has basically battery requirements and has to live in remote locations. Maybe that would be something that you would basically go and design with a very minimal compute and therefore minimal software, because it's doing something minimalistic and then not doing a lot of processing. But then it will be many of them that are out there. So the scale kicks in, and so it also fits into your pricing model at that point. And you might want to install it in constrained locations where the real estate might be an issue where you want to put it. So you might want to go with more smaller designs, and then obviously software accompanying it will be small too. And then you might not have a very rich set of operating system primitives that you might want to use, but you might go with something like a RTOS or maybe even a simple bare metal app. But then if you have more or less a connected device that does processing, or maybe some data serialization, data management, then obviously you go with more like a single board computer kind of design or maybe a system on module kind of design and have full operating system, perhaps embedded Linux or others, and then have your application stack on top. So that's my take on it. So what's your take?
Yeah, that's just thinking back to some of my experiences. I remember years back, we were working with a customer. They were designing a terminal, a touchscreen terminal that would be used inside of a tractor to instrument some equipment they were pulling behind it. And we were talking about screen sizes, and eventually they kind of settled on a VGA, 640 by 480 VGA touchscreen display. And, they were originally planning to drive this thing with a PIC microcontroller because that's what they were used to. They use PICs in all their products, and they work great. But when we started looking at the bandwidth requirements, even a modest VGA display, unless you have a LCD controller and a good bit of memory, there's just no way to do it with a PIC, at least a low-end PIC. Maybe the newer ones would do it.
Right.
So coming from an embedded Linux background, it was obvious to me that we use something like an ARM processor that has, that runs Linux and has a LCD controller built into it. So that's just one example. If you have a reasonably large touchscreen display that you need to display quite a bit of data on, then that kind of pushes you towards embedded Linux class system. And then, like you mentioned, anytime you're handling, say, more than a couple sensor values, say you have a system that's expandable to a number of sensor nodes, or that's collecting a lot of data at a fast pace and needs to manage that. That's another case that calls for Linux. And then the third class of device is what you already mentioned, is a connected device where you need connectivity to the internet. And that's your typical IoT scenario, where you have a system collecting data and then sending it to a server using a cellular modem or Wi-Fi or whatever. So those are kind of the three classes of devices that I think really are served well by embedded Linux: the large display, handling lots of data, and then connectivity. So those are kind of the three general categories that I see.
Yeah, I think that's well put. I think, largely you could classify those into these categories. And then obviously, as you mentioned, there are more constrained systems that you could go down where Linux probably wouldn't make sense. But you might want to go with either a real-time operating system or just a bare metal app that you might want to run on those devices. And there are few RTOS options out there that will fit into those. Typical example could be a smart bulb or something. All it will have to do probably is few operations like turn on, turn off, maybe change colors or what have you, few other operations. So you really don't want to put embedded Linux on that control those bulbs. So essentially, that I think my take on the fourth category that you will not want to do embedded Linux on. So I think once you have your kind of system ready, there is another aspect of it, and I think that's around programming languages. And in many cases, people are very vested into languages, and I've seen in my career wars fought between various languages.
Yeah, that's
and and maybe there is a reason for that. And it's always good to be passionate about things, and I really appreciate that. I came from a compiler background and operating system backgrounds, initially doing compilers. And one thing I learned early on is that all these languages are like tools in your toolbox if you were a plumber or something. And better to know which tool to use where rather than take one tool and try to use it everywhere. And this was a learning I always carried on with me. So I was primarily working on C++ compilers, but then having that perspective made me adopt various other language paradigms. So I think in this context, what's your take on the languages for embedded programming in general? So leaving aside, you have the system which is the embedded Linux system, and it will have components that are already programmed and written in specific languages. So it may be a combination of those language runtimes that your embedded system may have. But in particular, when you are designing your embedded Linux application, what are your thoughts on various languages from that aspect?
Yeah, maybe we could just go down through a list here. And I guess I'd probably start with C. That's kind of the oldest, most basic programming language. Linux kernel's written in it. Most of the basic libraries. So yeah, it's very possible to write your applications in C. My experience is if you start in C on Linux, you typically at some point move to C++ so that you can use classes and that. It kind of helps organize an application. And that's a reasonable option. There are tons of libraries available to do about anything, and that's really another one of the big advantages of embedded Linux is there are so many libraries out there, and about most of the libraries that will run on your desktop system will also run on your embedded Linux system. So really being able to leverage all that work and pull that functionality into an embedded application is really neat. So there's obviously some downsides to C and C++. It's just a little more tedious to write the code because you have separate source and header files. And years ago we didn't think that was a big thing, but after you've programmed in Go or Python or one of the newer languages, you kind of realize that's not really needed. And probably the other big problem I've seen in C and C++ programs is the lack of memory protection and just general. You have to be very disciplined and very careful. Otherwise, you'll end up passing a null pointer around and something else will try to use it and the app will crash. And one of the worst experiences is you write an application, you test it extensively, and then you start deploying it into the field and it's crashing and you don't know why. And it's very difficult to instrument C or C++ applications in the field because, when they crash, they don't have a stack trace in the logs.
Right. Or
at least that's not without some work. So you typically have to try to collect a core dump and then bring that core dump back and run a debugger on it against the actual code that you deployed. So everything has to match up, and it requires a good bit of infrastructure and expertise to do all that. So to me, that's a significant disadvantage of deploying C and C++ in an embedded Linux system.
Yeah.
It's one thing if it crashes on your desktop, but when it's, 500 miles from you and it's crashing and you don't have physical access to the device, it's a bad situation.
Yeah, I completely agree with you. So, I think C being one of the oldest languages always had that advantage of having enough infrastructures, and then C++ came, and so there has been a year of languages in 90s when you got like Ruby, Java, Python all coming in like almost in the same year, I believe. So what's your favorite language right now if you were to program an embedded system today for Linux, as for embedded Linux in general?
Yeah, it's hands down Go. So I started with Go probably 3 or 4 years ago, and we've done 3 or so projects in it now, and it's been an amazing experience. And I'll just compare it a bit to like Python. One of the big advantages of Go is it has a very efficient and small runtime. So that's the garbage collection and other bits or other pieces that make the language run. And typically with Go, you just embed the runtime right in the application, and it's pretty small. Like a minimal Go app will be 2 megabytes, and a large one might be a 10 megabyte executable or something in that range. So while that seems kind of large in the context of an embedded system, if you look at the alternatives like Java or Python, each of those environments requires a significant runtime that also needs to be deployed to the target. All kind, there's just hundreds and hundreds of files if you want to deploy Python or Java. And where a Go application, it's just one file, one executable, has the runtime embedded. It's relatively small, and the deployment experience is just wonderful with Go because there's no, it's one file and you're done.
So could you talk about if you were to write something, in C++ or other, like maybe Python, and then you were to do that in Go, what would be your developer experience? How would you compare and contrast the developer experience, leaving aside, what the final output would be that you will be able to run on the system? Because obviously there is a developer who is involved in, doing all the algorithm design, coding, and everything. So what's your take on that one? Given the Golang ecosystem, could you talk about what are the benefits of Golang and what are some of your favorite pieces as a programmer?
One thing to understand with an embedded system is typically it's a different architecture, namely ARM, than your desktop PC, which is x86. So that means the applications typically need to be cross-compiled if they're compiled for your target architecture. So with Java or Python, you would have to cross-compile it or anyway a runtime for your target embedded architecture. Go has the built-in ability to cross-compile to about any hardware or any architecture like x86, MIPS, ARM, maybe some others as well. And it's as simple as setting an environment variable named GoArch. So if you set that to ARM or ARM64 and then just run your build, it magically spits out an ARM binary and you copy it over to the target and it just runs. And if you contrast this with the cross-compile experience in C or C++, you'll if you have any experience at all with that, it truly is amazing. Tooling has made it so simple to do things that in the past were pretty hard.
So Golang in general, I think, is kind of thought of as a web programming language, or rather a language for servers, and that's not it. It is for in general, but that's the impression when you go to anyone. They say, I'm doing backend programming, I write in Golang, right? So some people have started to form that opinion that this is a language for your more like serverish kind of workload. So how would you like to take this myth on?
Yeah, that's interesting. I guess Go is considered the language of the cloud, like you've described. Coming out for the cloud, it's written in Go.
Right.
Years past, it might have been written in Java. But today, any startup that's doing something in the cloud, or I should say most of them, they're writing applications in Go. And the reason Linux, I'll just kind of draw a parallel with the Linux operating system itself. The reason Linux has been so successful in the server space is it's very efficient, it's very configurable, it's very stable, and in the server space, if you can minimize your resource usage a little bit, you can save money, because if you're scaling to many servers, every little bit you can be more efficient. So the Linux kernel has kind of maintained a very efficient, non-bloated type implementation. And that may be changing some a little, but in general. So that same approach, especially if you compare it to like Windows or other operating systems that don't have that focus, because the Linux kernel, or the Linux kernel and the Linux operating system works so well on the server, those same attributes make it an excellent fit for embedded systems. It's efficient, it's reliable, it's small.
Mm-hmm.
And I think the same thing applies to Go. Go was designed to be very efficient, reliable, very easy to deploy in the server space or the cloud space. And those same attributes make it an excellent fit in the embedded Linux space. And I'll call, these might be termed edge devices today, would be a kind of an IoT device kind of at the edge that does some smart things.
Mm-hmm.
So that's kind of why I think Go has turned out to be such a good fit.
Mm-hmm. So I think that's well put, and actually, that's a good analogy that I personally haven't thought about, and I think it's a good one because it's more of the characteristics that you're looking for, driving into the embedded systems rather than specific technologies. So, and it does resemble to a lot from the Linux kernel aspects. So, are there any improvements in Go language or in Go compiler or any Go ecosystem that you found that could have been done better? I know that it's a fast-paced ecosystem that's always upcoming with new technologies or new additions to the ecosystem. But any one particular area that comes to your mind that still needs to be addressed?
Yeah, one thing with Go is it doesn't use the same application binary interface as C, so it can't easily use C libraries. That can be either looked at as an advantage or a disadvantage because the minute you start using C libraries in your Go applications, you're introducing all the problems that are associated.
Mm-hmm. So
what's happened in the Go space is or a lot of the functionality has been rewritten natively in Go.
Mm-hmm.
So if you really want to retain the advantages of Go, you need to keep your applications all pure Go.
Mm-hmm.
Otherwise, you start to lose the benefits of Go. And
Mm-hmm.
one simple example might be SQLite or SQLite, which is a very
Mm-hmm.
popular database for embedded systems, and it's excellent technology. It's used in Android, and many applications in the past have used SQLite to store data.
Mm-hmm.
And it's a C library, so you can use SQLite from Go. There are libraries and bindings. Your Go app is no longer easy to cross compile. It's no longer easy to deploy, and there's dependencies. So that's kind of the trade-off with Go. And I guess in my experience, I felt that you can find Go implementations of about everything you need. So it to me, it's not a showstopper, but you have to be aware of that.
Mm-hmm.
And I guess the other thing where Go is somewhat lacking would be in graphical toolkits. So
Mm-hmm.
there are bindings to Qt and other technologies, but it's not a graphical applications are not what the Go developers prioritize. So
Mm-hmm.
it's better for headless or IoT applications
Mm-hmm.
like that.
Right. So when we talk about Go, and we don't talk about Rust, that would be it never happens. So does Rust have any future in your mind in embedded?
Yeah, I've not done any significant Rust programming, so I'm no expert on Rust.
Mm-hmm.
But I believe where Go shines is it's a very simple language, and it is very simple to program in, but yet it's extremely reliable.
Mm-hmm.
Maybe not as reliable as Rust, but it gets you the 98% there,
Mm-hmm.
and it's a lot less overhead to program in, because it has garbage collection. It takes care of that for you. The channels and other features are very simple. The type system is easy to use.
Mm-hmm.
Interfaces are brilliant, but yet they're simple. So to me, it's a much easier language to program in. People can come up to speed on it faster.
Mm-hmm.
And if if you're willing to live with a couple megabytes for the runtime and the binding issues with C libraries and other things, for the average case, I think it's just a little better fit. But that may change over time. I don't, Rust.
Mm-hmm.
It seems like in applications that were traditionally done with C and C++, Rust may be a better fit there because it would produce the same type of executable output.
Mm-hmm.
What are your thoughts? I know you've looked at Rust and have worked with some teams that are using it, so you've kind of been able to watch that a little bit.
Yeah. So I think Rust in general, I think, has been relatively new on the horizon. And mostly I think what I see it as a systems language for the future. So, you go somewhere and you hear people saying that C has a space in the system. C is the system programming language. And I think moving forward, we have a solution in Rust, which basically could be that language that basically fits in the modern programming paradigm, gives you the benefits of memory safety and others, yet gives you same kind of executables like you got with C. So I see it being used perhaps if you want to write bootloaders or kernels in future. Then I think Rust is a compelling alternative that's out there. And there may be more, ecosystems out there which may be experimenting with it. So, but I think, it does have a place and a role to play in upcoming embedded Linux space. And I think it will basically be a bottom-up where, people will start producing those small, maybe bare metal apps that were written in C-based RTOSes, and then maybe some of bootloaders and kernels and features of that sort would probably be using Rust. So interesting times. I think one of the downsides I saw in there was that the compiler is quite slow, and error messages are quite cryptic. It reminds me of C++. So,
well,
so nothing is always shiny. There always are problems, but in the end, it solves a problem because, if you look in today, I think I read somewhere and that in embedded space programmed using C, C++ or other static languages, you had around 55 to 60% of issues coming were memory related, right? Buffer overflows, memory corruption, heap corruption, you name it. So, so it does solve a existential problem for those systems. And if say they were not powered enough to have a garbage collector or a more of a runtime, maybe it does stand a good lucrative option for these systems. So that's my take on it. I'm probably expecting much more like bootloaders, RTOSes, and perhaps kernels, who knows, in future, which will be written in Rust.
Mm-hmm. So, yeah, that sounds right to me, and I could even think like maybe system update components,
mm-hmm.
things that you want to be very reliable, but yet it's not the main application of your system, so you don't want a lot of bloat or.
Yes.
Yep. So that brings up a thought. The Go compiler is so fast. I mean, it. In any app I've worked on, it's just a few seconds to compile. So that's definitely refreshing coming from C++, where it might take. One application I worked on, I think it was taking 10 minutes or something on a quad core to do a complete rebuild of one application.
Mm.
And, that's significant. That really starts to eat into developer productivity and happiness. So that's another area Go really shines.
Mm. Yeah, I totally agree with you there. So I think having a proper language and obviously using it as a tool is critical at that point, and understanding that what your application is going to be, it might also weigh into your choice, and obviously what kind of developers you have access to is also very, very important.
Mm-hmm.
So if you were kind of like, through these steps, so what are some of your tips on structuring your applications for embedded Linux systems?
If you don't mind, I'd like to back up and talk about JavaScript yet, because I think we should.
Sure.
Maybe we should share a little bit about that, our experiences, mainly because JavaScript is probably the most popular language in the world right now. More people are programming JavaScript than anything else, and Node.js is very popular on the server.
Mm-hmm.
So, a natural tendency might be, hey, we know JavaScript. There's lots and lots of programmers that know it. So why don't we write applications on using JavaScript for embedded Linux? So what are your thoughts or observations on that?
Yeah, it's interesting. I think I almost forgot about it because I wanted to. So one of the systems that I was involved in had a design decisions made to write their application, the main application that did the management on the system using JavaScript. And sure enough, it's a quad-core, dual-core ARM processor, and it's almost like an edge device, and it has enough flash in there, so you could basically have something like JavaScript in there. But we found it was very difficult to have a static footprint of these systems or the dependencies. So essentially, writing it was quick, but when you are building a system for ARM, an embedded system, you're doing cross-compiling, and from shipping point of view, you want to lock your dependencies and you want to build them instead of fetching them from somewhere. So you have reproducibility, right? You want to ship the same version of that dependency module that came in. And it was quite hard because many modules weren't cross-compile friendly. And so in the end, what the development team ended up was basically doing native development on that ARM board. Mm-hmm. So basically here you have a x86 based system from 90s, maybe in terms of power and capacity the system could do. And then you are doing development on that. In my opinion, that is a step backward, right? And of course you are getting an experience of a native development, but I think your time is spent in dealing with a slow system. And obviously that system is not meant for development. It is meant for something else. So that was one thing, but more surprisingly, it was an embedded system. We were using OpenEmbedded to build it, and figured out that our image sizes are going into gigabyte plus, right? So I said, well, at a certain point of time, you need to distribute this system over a network, and having small image would be good. And start to look at it, you would see that I was surprised to see half of the dependencies in the size were because of this application pulling in almost the whole world. And it was seen, but there was no easy way for us to remove those dependencies because many of them were pulled in they were more indirect dependencies that were pulled in. So there was like a tree of dependencies that kind of was easily going out of control.
Mm-hmm.
So I think what my learnings there were that it's easy to start, but it's a slippery slope unless you have toolings and kind of checks and balances in place where you are like taking a very hard look at what those dependencies are, the ones that are being pulled in, and then you need to have a reproducible build system so you can basically go 10 years from now and then still build the same app. So I think those were kind of things that I found interesting from deployment aspect, it was not as pleasant as I would have expected it to be.
I have one customer who they hired a contractor to build an app for them, and the contractor chose Node.js.
Mm-hmm.
And they got it all working, but when we went to deploy it on the embedded system, one of their NPM dependencies was pulling in some native code. And once you start digging into these native integrations in these NPM modules, it's just a disaster, because there's no consistency, or at least back when I looked at this problem, there was no consistency in the way people did things. They would just write all these scripts and things that would download various bits of libraries and run the C compiler and do this and that. And, it barely works on an x86 system, but the minute you try to cross... So we actually ended up doing the same thing you mentioned. I think we set up a Raspberry Pi or a BeagleBone with Debian.
Mm-hmm.
We actually built the NPM dependencies, copied the binaries, to a tarball, and then we actually used those in Open Embedded to deploy. And we had a number of other problems. We needed a certain version of NPM and Node, and those only existed in a certain version of Open Embedded, which would only work on which would only build on certain host operating systems, which wasn't what the customer was using. So that led us to using Docker. So you can see the whole thing just snowballed into a huge amount of work once you got to deploying.
Right.
So that's why Go has been such a refreshing experience when I compare it to experiences like that.
Right. Yeah. I think I wouldn't recommend JavaScript for these kind of environments, and it's better to take that decision early on and then basically take a wrong decision and spend the rest of time proving it's right. And I think that's kind of your fighting wrong battles. So obviously it's a good starter, as a lot of ecosystem out there, but then know your targets is always what is my learnings from it so far.
Yes, definitely.
Yeah. So I think let's talk about a little bit on the structuring your app, and what are some of the key tips during development that you would like that you have used so far for developing your embedded applications for embedded Linux.
Yeah, I'd say the number one thing to remember is embedded Linux is very similar to your desktop Linux or your server Linux, at least with Open Embedded built distributions. If you get into something like OpenWRT, then that's completely different and very custom. Mm-hmm. So I wouldn't say it would apply as much there, but with an image built with Open Embedded, you have a Linux environment that is very similar to your desktop environment. Mm-hmm. Application development experience is very similar. The tools and things you have available are very similar. You can SSH into your embedded system. You can run commands just like on your desktop system. What I found myself doing is doing most of my application development on a workstation, on a Linux workstation, mm-hmm. and then doing most of my development there, most of my testing, and then kind of just deploying to the target for as kind of a final check. Mm-hmm. And that works really well because, development is fast on your desktop. There's no deployment step. You just build it and run it. Mm-hmm. And if there's things like I/O, you can simulate the I/O, or if it's on a standard bus like RS-45, you can sensors to your PC instead of your embedded system. Mm-hmm. And, the graphical libraries are the same if you're using Qt, so you can run your graphical app on your desktop system and it'll look the same. So this is really a huge win for embedded Linux because it improves the developer efficiency so much compared to a completely different environment like an RTOS would be, where you have to deploy to the target every time you want to do anything. So I guess that's kind of the mindset I encourage, kind of plan on the outset for being able to build your app on a PC or for your target. And that'll give you a lot of flexibility, and it'll also encourage you to structure it in a clean way so there's not a lot of tangled things that are
right. Yeah. So any kind of ideas around like unit testing, and would you kind of also include that in your design early on, and have any sort of integrations right from day one when you write it down for your testing, or what have you done there in this area?
Yeah, I think unit tests are great, especially for algorithms, where you are developing something that's pretty complex. A lot of your development may be more I/O related, which is not as easy to unit test. You're more just trying to get data from point A to point B. But definitely for algorithms and complex bits of code, if you unit test it, you'll end up with a cleaner, and it's also a lot of fun. I mean, unit tests are just fun, so.
Yeah. I think the other areas essentially I've seen is that, you are designing your systems for remotely, working in a remote scenario, and, you'll have ways to interact with it. And one of the things that I learned is for like telemetry and control, basically having a robust logging mechanisms in place is really helpful. And, for if you want to go further, maybe, include some tracing infrastructure that you can enable either remotely, or maybe, give more a build that has tracing enabled as well. So I think that goes a long way from not only developing when you are in the development phase, but also when you're in a deployment phase. So what I've seen is that people have tried to retrofit these ecosystems or these kind of infrastructures into existing frameworks, and that becomes quite a bit involved process unless you have thought about that early on. So, having that in mind, like simple things like maybe, can I use a debug version of malloc, maybe, just an example, right? Can I kind of build that into my application? So, with one switch, I could just debug if there is something wrong going on there, or maybe I can have levels of messages that are coming out of my application. So I could bump that to 7 and make my application very chatty, and thereby know the characteristics of the problem. So I think that one thing I'd like to add here from my end, that it's important to put that into the structure.
Yeah, that's for sure, because if you're debugging a hard problem, most of the time the way you figure it out is through a log, where you can see what's happening over time, because the really hard problems aren't just a logic error, at one place where you can single step through the code and see the problem. It's more of interaction between different parts of the app and how those interactions happen over time, and really logging or tracing, like you mentioned, is really the only way to effectively debug really hard problems. So yeah, I agree. Being able to turn on these log levels is a really valuable tool for a complex application.
Yeah. So I think it is kind of, the structure is kind of, I see it as a main thing that you have to put together as a design, and then supplement it with certain tools that, you can integrate into your workflow, or maybe run them occasionally, but have a easy way to offer them to your workflow. So in that, I think one of the interesting thing is always about code editing, and there has been IDEs and whatnot in place, and over a period of time, different people use different IDEs or editors, and it's similar to I mentioned earlier about choosing a language. Even there are editor wars, and that you will see out there on the internet. So what is your favorite code editor these days, and why do you like it?
Yeah, I'm still using Vim, or NeoVim specifically.
Mm-hmm.
And overall, off and on, I've tried things like VS Code or IntelliJ, and I like those a lot. They're great tools, and people are doing amazing things with them. And oftentimes the level of automation and code, IntelliSense and all that is actually better in those tools. But I guess I just kind of keep coming back to NeoVim or Vim just because it's a little faster.
Mm-hmm.
It just kind of feels a little more connected to my fingertips as I'm editing the code. And to me, that's kind of an important to have that kind of almost connected feeling, that when I do something, it just happens without any delay or any. And I guess the other thing is I do a fair amount of server administration, so it's useful to know an editor that's going to be on every Linux system you'll ever touch,
right?
To be efficient at that. So how about yourself? What editors are you using these days?
Yeah, so I was a Emacs user a long time ago at university, and then once I started working on embedded systems, then Emacs is not there, so I learned VI, and then some variants of VI were always available, and that was good because I was working on FreeBSD systems, Sun systems, Linux systems, and one thing that was common was VI. So that was really good to learn VI, and I still use VI predominantly to do a lot of my administration work, as you mentioned, logging into remote servers and editing code as well. But I've started to like VS Code quite a bit, and I've had my interactions with Eclipse and Scintilla and others over a period of time. Notepad++ and a few other editors are there, and I tried Atom for a while as well. But I think all these Electron apps, I think VS Code by far is my favorite these days. I keep finding new and new things, that is supported in their marketplace that you can download, and I think all the linters and they just supplement your workflow quite a bit, and I really like that. So most of the time I'm doing Python, then I have all the Python linters in there. I'm doing C++, there's a Clang format and everything in place. So it gives a richer set of experience for me, from that aspect. That all those tools are integrated, I really don't have to worry about running them myself, so it just shows up in the editor. It's quite intuitive from that aspect.
Yeah, it is amazing how easy it is to really quickly get an environment set up in VS Code that does everything, code formatting, linting. And also VS Code has a decent VI emulation. So if you like the VI.
Yeah.
Mm-hmm.
Cool. So I think what are some other debugging techniques that you use in general for once like you have your structure in place and you are developing, you're using your favorite language and tools in place? What other tools or debugging techniques do you deploy?
Yeah, I guess I'm kind of an old school printf type guy, where if I need to debug something, I typically just put in a print statements, or if we want to act a little more sophisticated, we could call that logging. You could have a little more elaborate logging framework.
Yeah.
So I guess I feel that you should be able to write code that most of the time it runs mostly correctly, and if there's a small amount of debugging needed, a printf is adequate. So I've rarely felt the need to have debuggers in the traditional sense where you single step through the code, or something that an RTOS developer would be very used to. So that may be I don't know if most embedded Linux application developers are that way, but the fact that the Linux kernel has really never had tight debugging support, it's kind of a culture. And I think it's more of a symptom of very complex applications. You really can't afford to be single stepping through an app. The problems you're trying to solve are are so much bigger than what you can debug by just looking at a tiny little piece of the code. And if you're writing some really tricky code, that's where a unit test comes in. Unit test it and debug it with a unit test rather than in the context of the whole app.
Yeah, and that's far quicker and turnaround than if you were to do the wholesale setup. Yeah, this comes to like once Linus Torvalds said that I need more eyes to look at the code rather than more tools, and I'll have less bugs.
Mm-hmm.
It's actually very true. And I think it reminds me once trying to debug a video app, and it used Qt WebKit, and so there was actually a crash. We said, well, we have GDB server. Why don't we basically try GDB server, on the target? And locally, it was difficult to set because the device didn't export IP address, and so doing it over serial, there were other challenges because the device was in a different location. So we said, well, why don't we put debugger right in the image and onto the target? Sounds simple. We did that, and we launched it, right? And the crash happened, but nothing would show up on the target, and it was always busy. It took probably, I don't remember how many hours, but probably in the range of 2 to 3 hours for it to come back with a stack trace. Because, number one, this is a big application. Stack trace is deep. And I think if the tool is coming in your way, right, that, it's giving you a time to, okay, now tool is loading, it's distracting from a developer point of view. So tool should be just doing the work in the background and not even you don't even have to think about it. So I found that that's not always the case, especially in the embedded space with all these tools. Even though they are pretty popular on native apps, and if you have like really powerful devices, then I think it probably makes sense to look through them. But again, as you mentioned early on, all this will require a lot of infrastructure to either dump the stack traces, bring them over, have your debugging for mapped, if you want to do it in a cross environment, or if you want to ship debugger right on the target, then your target has to be able to run and be able to look through it. So, so essentially, I think this is important, but we have to know the constraints where these tools can fit in.
Yeah, that's one of the huge advantages of Go is if it crashes, you see a stack trace, so that those can be captured in logs. There's no infrastructure required. That's just part of the runtime. And historically, the only time I've really ever used GDB is to debug crashes, and get a stack trace. Mm-hmm. But when I talk to people who are just coming into embedded Linux, the first is I want to be able to remotely debug, as in single step through code on my target. And in my experience, I just really haven't found that as all that necessary or useful. It could be handy at times, but it's not an everyday thing that I'm using all the time. So in my experience, it rarely justifies the work to get all that working. If you have a good story where you can develop your apps on a workstation and so on. Yeah.
I have a different take on it as well. A lot of times, like developers, they kind of learn by doing, so to speak. What they do is they put the code through the debugger and see what debugger is printing, and so they kind of reverse engineer the logic and then try to learn through those. And those are really bad practices in my mind, because many times you create code that is dependent upon the compiler and a certain behavior from the compiler that may not be even, valid in the next version of the same compiler, let alone, a different compiler. So I think it kind of, I've seen that kind of use case as well prop up with, all this debuggers. So I think that definitely produces a code that definitely won't be portable as well. So that is a side effect that you can see in many, many cases as well.
Yeah, that's a good point.
Right. So, so should I worry about optimizations?
Yeah, that's one application we worked on. We did a lot of profiling because, we were kind of pushing the system right at the edge with handling tons and tons of mapping data.
Mm-hmm.
So, but for a lot of the other projects I've worked on, a 500 or a 1 gigahertz microprocessor unit is quite fast. And, unless you're doing something pretty complex with a lot of data, often you have more than enough computing power. So as long as you're a little bit careful about writing your app,
mm-hmm.
and not have a lot of loops just spinning and things like that,
Yeah, I think I would agree with you. Like in the past, and compilers have become smarter too. We have to take that fact also into
mm-hmm.
account. So, you had these smarts in the past, like, you go for an interview somewhere and somebody will ask you, how efficiently can you flip the bytes, in a word? And, you will do those smarts about, shifting left, shifting right kind of thing. And they will ask, without using a temporary variable, how can you transfer the content of one into another? All those little tricks are now people optimizations in compilers, right? So compiler will figure it out itself. Whether that's a Go compiler or Rust or, underneath it's LLVM for Rust. So they are very sophisticated compiler optimization infrastructures that are helping you underneath. So you could concentrate on writing the logic and don't worry about those little things. And I know that even today people are very excited about, compiler optimizations, and that's good. But I think, spending too much of time, it's that Pareto's principle of 80-20, and I think you have to know where you need to spend your time in terms of, and I think if you put a good logic and good implementation into your algorithm, compiler will do the right thing. And actually one thing it really does good is if you have simple code, then compiler has better chance to optimize it. Mm-hmm. It's as simple as that. So if you write like A is equal to B, and don't use those NOR and XOR operators to, shift the content. Instead, you define variables like, okay, I move this into that into this, like how you would think. The end result would be far better than if you came up with a very smart construct and confused the compiler as well. Because remember, compiler has heuristics, right? So if heuristics fail, then it has to resort to a more conservative approach, and that would be to generate a less optimized code because it didn't really understand what your code construct was. So I think it's important from that point that see whether the tool is doing the right thing for you. Help it by writing good, simple code.
Yeah, that's very interesting. And I guess I should also just mention, if you run into performance problems and you're kind of running right at the edge of the capabilities of your hardware, that is a huge time sink and consumes a lot of resources and time if you're always kind of right at the performance limits of your hardware. Mm-hmm. So I would say one of the most important things to do when selecting hardware is make sure you have enough performance that you're not bumping up against the limits of your hardware, because that's a very difficult situation to deal with.
Very rightly said.
If you can have some margin, some headroom, it'll make your project so much easier and so much more pleasant, so.
Yeah.
Yeah.
So, I think having all that in place, I know that, you have worked on various frameworks and toolkits. And so before we end today's discussion, what's your take on what are the interesting, toolkits and frameworks for embedded Linux application development that are out there or, have been around or are future?
Yeah, I guess for graphical toolkits, Qt seems to be one of the main ones today. In years past, we used the GDK toolkit as well, but that doesn't seem to be very, very popular anymore in an embedded Linux. Mm-hmm. So I guess if you're used to those types of toolkits and that's what you want, Qt seems to be a good way to go. The other thing we've done with graphical applications recently in several projects is to actually run a browser full screen on the LCD, and then write a web application that runs in that browser and talks to perhaps a Go backend also running on the embedded device. And that also works pretty well because web programming skills are very common, and it also allows you to access the application remotely with a browser on any device.
Right.
So that's a scenario where more of a web development type user interface application makes a lot of sense.
Right. All right. So I think that was our talk for today, and thank you. Anything else you would like to cover?
Yeah, I just had one other thing that crossed my mind as we were talking, and that setting up your editor to do auto formatting and linting automatically.
Good one.
I learned about auto formatting from the Go auto formatter, and for that I just had to have it for all the languages I work in, and it's really been a significant change in my code editing experience. So it may not seem very important if you've never tried it, but I would strongly encourage people to try auto formatters, because it's just one more thing the compiler or the computer can do for you. There's no reason you should have to worry about indenting and, is this formatted right? You just write your code and save it, and boom, it auto formats it. So
yeah, I think it's a very, very important point, because many times auto format also tells you about the syntax errors that compiler will throw at you. So
sure, right, exactly.
So I think I'm a huge fan of these tools, and and code linting, and that's where LLVM shines, at least in C++ area. They have Clang Tidy and Clang format, for if you're writing C++ code, then you can deploy those tools. But then you could also do other languages. There's a Python linter, pretty much I think all languages have those linters. And I think deploying those is pretty neat. And I think it also goes with our psychology, how we see structure visually. And I think it's much more productive to have that consistency encoded in the tool itself, that you don't have to worry about tabs and spaces. Hey, Python.
Well said.
That's one thing.
Yeah.
Anyway, so I think with this, I would like to thank you, Cliff, for sharing your thoughts. I think it was very educational for me, and I'm sure that listeners will like it too.
Likewise.
Right, thank you.
Okay, till next time. Take care.